They do add to 51. Step 3. Draw the histogram. Mark the scale for the variable whose distribution you are displaying on the horizontal axis. That's the percentage of a state's high school students who graduate within 4 years. The scale runs from 70.0 to 92.5 because that is the span of the classes we chose. The vertical axis contains the scale of counts. Each bar represents a class. The base of the bar covers the class, and the bar height is the class count. Draw the bars with no horizontal space between them unless a class is empty, so that its bar has height 0. Figure 1.5 is our histogram. Remember, an observation on the boundary of the bars, say 75.0, is counted in the bar to its right. Figure 1.5. Histogram of the distribution of the percentage of on-time high school graduates in 50 states and the District of Columbia. For example, 1.4. This figure was created with the ch1 software package. Number of states. Percentage of on-time high school graduates. This bar has height 6 because 6 states have between 77.5 and 79.9 on-time high school graduation rates. Although histograms resemble bar graphs, their details and uses are different. A histogram displays the distribution of a quantitative variable. The horizontal axis of a histogram is marked in the units of measurement for the variable. A bar graph compares the sizes of different quantities. The horizontal axis of a bar graph simply identifies the quantities or categories being compared and need not have any measurement scale. These quantities may be the values of a categorical variable, but they may also be unrelated, like the sources used to learn about music in example 1.3, page 18. Draw bar graphs with blank space between the bars to separate the quantities being compared. Draw histograms with no space to indicate that all values of the variable are covered. A gap between bars in a histogram indicates that there are no values for that class. Our eyes respond to the area of the bars in a histogram. Because the classes are all the same width, area is determined by height, and all classes are fairly represented. There is no one right choice of the classes in a histogram. Too few classes will give a skyscraper graph with all values and a few classes with tall bars. Too many will produce a pancake graph, with most classes having one or no observations. Neither choice will give a good picture of the shape of the distribution. You must use your judgment in choosing classes to display the shape. Statistics software will choose the classes for you. The software's choice is usually a good one, but you can change it if you want. The histogram function in the histograms applet in Achieve allows you to change the number of classes by dragging with the mouse so that it is easy to see how the choices of classes affects the histogram. Apply your knowledge. 1.6. The changing face of America. In 1980, approximately 20% of adults aged 18 to 34 were considered minorities, reporting their ethnicity as other than non-Hispanic white. By the end of 2013, that percentage had more than doubled. How are minorities between the ages of 18 and 34 distributed in the United States? In the country as a whole, 42.8% of adults aged 18 to 34 are considered minorities, but the states vary from 8% in Maine and Vermont to 75% in Hawaii. Table 1.2 presents the data for all 50 states and the District of Columbia. Make a histogram of the percents using classes of width 10%, starting at 0%. That is, the first bar covers 0% to less than 10%, the second covers 10% to less than 20%, and so on. Make this histogram by hand, even if you have software, to be sure you understand the process. You may then want to compare your histogram with your software's choice. Table 1.2. Percent of state population aged 18 to 34 who are minorities. So list the state and then the percent for each of the states. In the District of Columbia, 1.7, Choosing classes in a histogram. The histogram's applet in this exercise includes a histogram of the data on the percentage of minorities between the ages of 18 and 34 in the states from Table 1.2. Choose these data, and then click on the Histogram tab to see a histogram. A. How many classes does the applet choose to use? You can see the count of classes on the toggle button below the histogram. B. Click on the Classes toggle button and drag to the left. What is the smallest number of classes you can get? What are the lower and upper bounds of each class? Click on the bar to find out. Make a rough sketch of this histogram. C. Click and drag to the right. What is the greatest number of classes you can get? How many observations does the largest class have? D. You see that the choice of classes changes the appearance of a histogram. Drag back and forth until you get the histogram that you think best displays the distribution. How many classes did you use? Why do you think this is best? 1.4. Interpreting histograms. Making a statistical graph is not an end in itself. The purpose of graphs is to help us understand how the data help us answer some real-world question. After you make a graph, always ask, what do I see? Once you have displayed a distribution, you can see its important features as follows. Examining a histogram. In any graph of data, look for the overall pattern and for striking deviations from that pattern. You can describe the overall pattern of a histogram by its shape, center, and variability. You will sometimes see variability referred to as spread. An important kind of deviation is an outlier, an individual value that falls outside the overall pattern. One way to describe the center of a distribution is by its midpoint, the value with roughly half the observations taking smaller values and half taking larger values. In Chapter 2, we will formally define the midpoint as the median. To find the midpoint, order the observations from smallest to largest, making sure to include repeated observations as many times as they appear in the data. First cross off the largest and smallest observations, then the largest and smallest of those remaining, and continue this process. If you initially had an odd number of observations, you will be left with a single observation, which is the midpoint. If you initially had an even number of observations, you will be left with 2 observations, and their average is the midpoint. For now, we will describe the variability of a distribution by giving the smallest and largest values. We will look at better ways to describe center and variability in Chapter 2. The overall shape of a distribution can often be described in terms of symmetry or skewness, defined as follows. Symmetric and skewed distributions. A distribution is symmetric if the right and left sides of the histogram are approximately mirror images of each other. A distribution is skewed to the right if the right side of the histogram, containing the half of the observations with larger values, extends much farther out than the left side. It is skewed to the left if the left side of the histogram extends much farther out than the right side. Example 1.5. Describing a distribution. Look again at the histogram in Figure 1.5. To describe the distribution, we want to look at its overall pattern and any deviations. Shape. The distribution has a single peak, which represents states in which between 87.5% and 90.0% of students graduate high school on time. The distribution is skewed to the left. There is only one observation to the right of the peak, while to the left of the peak, most of the remaining states have graduation rates between 77.5% and 87.5%, but several states have much lower percents, so the graph extends quite far to the left of its peak. Center. Arranging the observations from Table 1.1 in order of size shows that 86.0% is the midpoint of the distribution. There are a total of 51 distributions, and if we cross off the 25 highest graduation rates and the 25 lowest graduation rates, we are left with a single graduation rate of 86.0%, which we take as the center of the distribution. Variability. The graduation rates range from 71.1% to 91.0%, which shows considerable variability in graduation rates among the states. Outliers. Figure 1.5 shows no observations outside the overall single-peaked, left-skewed pattern of the distribution. Figure 1.6 is another histogram of the same distribution, with classes of width 2% rather than 2.5%. Now, New Mexico at 71.1% and the District of Columbia at 73.2% are more clearly separated from the remaining states. Are New Mexico and the District of Columbia outliers, or just the smallest observations in a strongly skewed distribution? Unfortunately, there is no rule. Let's agree to call attention to only strong outliers that suggest something special about an observation, or an error such as typing 10.1 as 101, although the District of Columbia is often included with the other 50 states in data sets. For many variables, it can differ markedly from the remaining states. Figure 1.6, another histogram of the distribution of the percentage of on-time high school students with narrower class widths than in Figure 1.5. A histogram with more classes shows more detail, but may have a less clear pattern. Figure 1.5 and 1.6 remind us that interpreting graphs calls for judgment. We also see that the choice of classes in a histogram can influence the appearance of a distribution. Because of this, and to avoid worrying about minor details, concentrate on the main features of a distribution that persist with several choices of class intervals. Look for major peaks, not for minor ups and downs, in the bars of the histogram. When you choose a larger number of class intervals, the histogram can become more jagged, leading to the appearance of multiple peaks that are close together. Always be sure to check for clear outliers, not just for the smallest and largest observations, and look for rough symmetry or clear skewness. Here are more examples of describing the overall pattern of a histogram. Example 1.6, Iowa test scores. Figure 1.7 displays the scores of all 947 7th grade students in the public schools of Gary, Indiana, on the vocabulary part of the Iowa test of basic skills. The distribution is single-peaked and symmetric. Real data are almost never exactly symmetric. We are content to describe Figure 1.7 as symmetric. The center, half above, half below, is close to 7. This is 7th grade reading level. The scores range from 2.1, 2nd grade level, to 12.1, 12th grade level. Notice that the vertical scale in Figure 1.7 is not the count of students, but the percentage of students in each histogram class. A histogram of percents, rather than counts, is convenient when we want to compare several distributions. To compare Gary with Los Angeles, a much bigger city, we would use percents so that both histograms have the same vertical scale. Figure 1.7. Histogram of the Iowa test vocabulary scores of all 7th grade students in Gary, Indiana, for example 1.6. This distribution is single-peaked and symmetric. When describing the vertical scale of a histogram, you will sometimes see count referred to as frequency and percentage referred to as relative frequency, particularly when choosing an option for the vertical scale using software. Example 1.7. Who takes the SAT? Depending on where you went to high school, the answer to this question may be almost everybody, many but not everybody, or almost nobody. Figure 1.8 is a histogram of the percentage of high school graduates in each state who took the SAT in 2018. Figure 1.8, histogram of the percentage of high school graduates in each state who took the SAT reasoning test, for example 1.7. The graph shows 3 groups of states: ACT states, where few students take the SAT, at the left, states where many take the SAT and some the ACT, and SAT states at the right. 3 peaks suggest that the data include 3 types of states. To create the histogram with bars covering only the range of 0% to 100%, we had to choose the class intervals wisely. A few states had 100% of high school students take the SAT, The lowest percentage is 2% for North Dakota. We would like to avoid having a class interval that begins at 100% and includes values larger than 100%, which is impossible, and would result in a histogram that suggests values larger than 100% in the data. We therefore use class intervals of 0.01% to less than 10.01%, 10.01% to less than 20.01%, etc. However, we have only displayed percents to the nearest integer on the horizontal scale. The histogram shows 3 peaks, a high peak at the far left representing percents 10% and below, a lower peak in the 60.01% to less than 70.01% class, and a high peak representing percents above 90%. The presence of more than one peak suggests that the distribution mixes several kinds of individuals. That is the case here. There are 2 major tests of readiness for college, the ACT and the SAT. Most states have a strong preference for one or the other. In some states, many students take the ACT exam and few take the SAT. These states form the peak on the left. In other states, some students take the ACT and some the SAT. These states are the bars near the peak in the 60.01% to less than 70.01% class. Yet in other states, almost all students take the SAT and very few choose the ACT. These states form the high peak at the far right. Giving the center and variability of this distribution is not very useful. The midpoint falls in the 50.01% to less than 60.01% class between the peaks. The story told by the histogram is in the 3 peaks, corresponding to primarily ACT states, states in which students take both, and primarily SAT states. The overall shape of a distribution provides important information about a variable, although describing the shape of a bar graph for categorical data is not useful. Some variables have distributions with predictable shapes. Many biological measurements on specimens from the same species and sex, lengths of bird bills, heights of young women, have symmetric distributions. On the other hand, data on people's incomes are usually strongly skewed to the right. There are many moderate incomes, some large incomes, and a few enormous incomes. Many distributions have irregular shapes that are neither symmetric nor skewed. Some data show other patterns, such as the 3 peaks in Figure 1.8. Use your eyes, describe the pattern you see, and then try to explain the pattern. Apply your knowledge. 1.8. The Changing Face of America. In Exercise 1.6, page 22, you made a histogram of the percentage of minority residents aged 18 to 34 in each of the 50 states and the District of Columbia. These data are given in Table 1.2. Describe the shape of the distribution. Is it closer to symmetric or skewed? What is the center, midpoint of the data? What is the variability in terms of the smallest and largest values? Are there any states with an unusually large or small percentage of minorities? 1.9. Lyme disease. Lyme disease is caused by a bacterium called Borrelia burgdorferi and is spread through the bite of an infected blackleg tick, generally found in woods and grassy areas. There were 386,846 confirmed cases reported to the Centers for Disease Control and Prevention, CDC, between 2001 and 2017, and these are broken down by age and sex in Figure 1.9. Figure 1.9. Histogram of the ages of individuals infected with Lyme disease for cases reported between 2001 and 2017 in the United States for males and females for Exercise 1.9. Confirmed Lyme disease cases by age and sex, United States 2001 to 2017. So you have the age on the x-axis in years and cases on the y-axis in thousands. And then you also have it divided by bars for sex, male and female, so the bars aren't touching. Here is how Figure 1.9 relates to what we have been studying. The individuals are the 383,846 people with confirmed cases, and 2 of the variables measured on each individual, are sex and age. Considering males and females separately, we could draw a histogram of the variable age using class intervals of 0 to less than 5 years old, 5 to less than 10 years old, and so forth. Look at the leftmost two bars in figure 1.9. The blue bar shows that almost 10,000 of the males were between 0 and 5 years old, and the green bar shows slightly fewer females were in this age range. If we were to take all the blue bars and put them side by side, we would have the histogram of age for males using the class intervals stated. Similarly, the green bars show females. Because we are trying to display both histograms in the same graph, the bars for males and females within each class interval have been placed alongside each other for ease of comparison, with the bars for different class intervals separated by small spaces. A. Describe the main features of the distribution of age for males. Why would describing this distribution in terms of only the center and variability be misleading? The distribution, the shape is bimodal and skewed to the right. The center and variability only wouldn't be helpful because it's bimodal, so it has two peaks, and the center doesn't probably show either peak. B. Suppose that different age groups of males spend differing amounts of time outdoors. How could this fact be used to explain the pattern that you found in Part A? Remember to use your eyes to describe the pattern you see and then try to explain the pattern. So the pattern is that males between 0 to 25 seem to get Lyme disease from being outside, and then males between 25 to 85 or 90 do, with a peak at around 50 years old. So that could tell us that males are going outside the most from 5 to 15 years old, and then they go outside the most again from between about 40 years old to 65 years old. C. A 45-year-old male friend of yours looks at the histogram and tells you that he is planning on giving up hiking because this graph suggests he is in a high-risk group for getting Lyme disease. He will resume hiking when he is 65, as he will be less likely to get Lyme disease at that age. Is this a correct interpretation of the histogram? He will still have a risk of getting Lyme disease at 65. It's just that less men at 65 go outside. So the correlation is probably between the amount of time you spend outside increases the likelihood of you getting Lyme disease. So that's like regardless of age. It just happens that men of different ages spend different amounts of time outside, and that's what gives you the variability in the number of cases per thousand. D. Comparing the histograms for males and females, how are they similar? What is the main difference, and why do you think it occurs? So it's bimodal for the females as well. And the shape is similar, but with a lower peak as the left peak and a higher peak on the right peak, whereas for the males, there's a higher peak on the left peak and a lower peak on the right peak when people are older. What is the main difference, and why do you think it occurs? The main difference is that more men in general get Lyme disease. The peaks are generally higher for both. This might be that men spend more time outside or males spend more time outside. But you can see females actually do get Lyme disease slightly more frequently after 75 years old to 90 years old. So maybe women go outside more frequently when they're older in those age categories. 1.5. Quantitative variables, stem plots. Histograms are not the only graphical display of distributions. For small data sets, a stem plot is quicker to make and presents more detailed information. Stem plot, a graph of the distribution of a quantitative variable. Each observation is shown as a stem, consisting of all but the final rightmost digit, and a leaf, the final digit. The unique stems are stacked in a vertical column, with the smallest at the top, and a vertical line appears to the right of the column. Each leaf for a stem appears in a row to the right of the stem. Stem plot. To make a stem plot, 1. Separate each observation into a stem, consisting of all but the final rightmost digit, and a leaf, the final digit. Stems may have as many digits as needed, but each leaf contains only a single digit. 2. Write the stems in a vertical column with the smallest at the top, and draw a vertical line at the right of this column. Be sure to include all the stems needed to span the data, even when some stems will have no leaves. 3. Write each leaf in the row to the right of its stem in increasing order out from the stem. Example 1.8, making a stem plot. Table 1.2, page 23, presents the percentage of adults aged 18 to 34 who were considered minorities in each of the states and the District of Columbia. To make a stem plot of these data, first write the percents 8 and 9 as 08 and 09 so that all the percents are two-digit numbers. Take the tens place leftmost digit of the percentage as the stem and the final digit ones as the leaf. Write stems for 0 for Maine, Vermont, and West Virginia, 27 for Hawaii. Now add leaves. Texas, 61%, has one leaf on the sixth stem. California and New Mexico, at 67%, each place a leaf of 7 on the same stem. These are the only observations on this stem. Arrange the leaves in order so that 177 is one row in the stem plot. Figure 1.10 is the complete stem plot for the data of Table 1.2. Figure 1.10, stem plot of the percentages of minorities aged 18 to 34 in the United States. For example, 1.8, the tens place of the percentage is the stem, and the ones place is the leaf. A stem plot looks like a histogram turned on end, with the stems corresponding to the class intervals. The first stem in Figure 1.10 contains all states with percents between 0% and 10%. Examine the histogram in Figure 1.11, which is a histogram of the minority data using class intervals 0% to less than 10%, 10% to less than 20%, and so forth. Although Figures 1.10 and Figure 1.11 display exactly the same pattern, the stem plot, unlike the histogram, preserves the actual value of each observation. In a stem plot, the classes, the stems of a stem plot, are given to you. Histograms are more flexible than stem plots because you can choose the classes more easily. Now, the professor would divide up the stems as well, so that's not totally accurate. Stem plots do not work well for large data sets, where each stem must hold a large number of leaves. Don't try to make a stem plot of a large data set, such as the 947 Iowa test scores in Figure 1.7. Consider making a stem plot of the high school graduation rate data in Table 1.1, page 21. If we use the tenths as the leaves, the necessary stems begin at 71 for New Mexico and end at 91 for Iowa, requiring a total of 21 stems. When there are too many stems, as in this case, there are often no leaves or just 1 or 2 leaves on many of the stems. The number of stems can be reduced if we first round the data. In this example, we can round the data for each state to the nearest percent before drawing the stem plot. Here is the result. So there are 3 stems, 7, 8, and 9, and 8 has most of the data points. Statistics in your world. The vital few. Skewed distributions can show us where to concentrate our efforts. 10% of the cars on the road account for half of all carbon dioxide emissions. A histogram of CO2 emissions will show many cars with small or moderate values and a few with very high values. Cleaning up or replacing these cars would reduce pollution at a cost much lower than that of programs aimed at all cars. Statisticians who work at improving quality in industry make a principle of this. Distinguish the vital few from the trivial many. Figure 1.11, histogram of the percentages of minorities aged 18 to 34 in the states, for example 1.8. The class widths have been chosen to agree with the widths of the stems in the stem plot in Figure 1.10. So you can see percent of adults aged 18 to 34 considered minorities on the x-axis, and number of states on the y-axis. So that's a count, and it's unimodal. There's one peak between 20 and 30 years old, and it's skewed to the right. Now it seems that there are too few stems. You can also split stems in a stem plot to double the number of stems when all the leaves would otherwise fall on just a few stems, as occurred when we rounded to the nearest percent. Each stem then appears twice. Leaves 0 to 4 go on the upper stem, and leaves 5 to 9 go on the lower stem. If you split the stems with the data rounded to the nearest percent, the stem plot becomes, and you can see 7 appears twice, 8 appears twice, and then 9 appears once, which makes the left skew pattern clearer. We're looking at high school graduation rate data. In fact, the stems in the previous stem plot correspond to the class intervals used in the histogram of figure 1.5, page 22, although there are minor differences in the histogram and the stem plot because the data were rounded for the stem plot, but not for the histogram. When drawing stem plots, some data require rounding, but don't require splitting stems. Some require just splitting stems, and other data require both. Many statistical softwares, such as Crunchit, allow you to decide whether to split stems so that it is easy to see the effect. A dot plot is another graphic for displaying small data sets.